Okay, yeah, so it's time. So on Wednesday, please, I hope you've already seen like the video I posted on Wednesday, because it's going to be a continuation, right? So do you have any questions for me from the video? Any issues? Okay, then let's continue from there, right? I'm sharing my screen. If you can't see, do let me know. So just a quick recap. On Wednesday, I talked about the fact that we are going to look at a new set of problems. Like for these problems, you're looking at calculating areas and distances, right? So I explained that this one can be likened to like computing the slope of a tangent and then the instantaneous velocity under when we started the differentiation, right, in 2.1, under section 2.1, right? So it's similar, right? So the idea was we're trying to calculate, say, an area under a curve, right? But then for a curve which has no defined outer shape, right? For example, if this outer shape here is like a rectangle, if the whole thing is like the curve is it's a horizontal line, right? And the area under it is like a rectangle, so you can easily compute that. If the thing is like it has an outer edge which is a circle, like a semicircle of some sort, then you can kind of use the area of a square to try and connect it and solve, right? Get the area under the curve. But if you have a curve which does not follow any, like the outer edges are not straight edge or not directly a circle, then there's a problem. You can't directly compute the area by likening it to any of the known area formulas that are already given, right? So what we did was we use rectangles to approximate the area, right? So we started by identifying the number of strips we need, right? So we identified the number of strips. So we are just dividing it into some sections and then calculating the area, right, within those sections. So we are creating rectangles from under the curve, right? So for this example, we're looking at 4 strips, right? So 4 rectangles to approximate the area under this, right? So what we did was we created equal width, which are sub-intervals. So for 4 strips from 0 to 1, the sub-intervals are 0 to 1 over 4, 1 over 4 to half, and then 3 over 4 to 1. And then we chose either, so the width are equal. And then we had to choose the height, because when you want to compute the area of a rectangle, you need like the length and then the width. So if you have the width, then we need, in this case, the kind of like, is a rectangle which is now standing up like so. So we already have the width. So how do we get the height? Now, to determine the height, we said we need to pick a sample point, right? And the sample point is just try and pick any point in between any sub-interval and use it to get your height, right? So we either use, for this one, the example was using right endpoints. So for right endpoints, for this sub-interval, you pick 1 to give you your height. So that's why we got this height for the rectangle. For this third interval, you pick the 3 over 4 to give you your height of the rectangle. So that's what gave us this. And then for this second one, we pick 1 over 4 to give us the height, right? And so on and so forth. Now we notice that, well, for one thing, when the function is increasing, then using the right endpoints will give you an overestimate, because you see that there are x-axis. You see the x-axis are there, right? Yeah, and then when the function is decreasing, then the right endpoint is going to give you underestimate. On the other hand, when the function is increasing, we can also choose sample points to be left endpoints. So for that one, just that we are picking left end to give us our height, right? So that's what you see here. But for that one too, there'll be what? There'll be like there'll be gaps in there which are not accounted for. Remember that you're trying to solve for the area under the curve, right? So there are gaps here, the one that I have the dotted reds on, right? So for that one too, is giving us an underestimate if the function is increasing. It will give us an overestimate if the function is what? Is decreasing, right? So we looked at that, but we saw that as the rectangles increase, then the x-axis for the right endpoints values are becoming smaller, right? So, and then the x-axis, and then the holes for the left, the unaccounted parts for the left endpoint values are becoming smaller. You see, so it's more like as you approach infinity, then you can see that you get the true area, because as the rectangles become a lot, right? As you increase the rectangles, you see that it's kind of like shrinking or accounting for all the area under the curve. So we said that the true area is the limit as n approaches infinity of the right endpoint or the left endpoint. So we established all of this, and then we talked about sample points and all those stuff, right? So we went through this. Another point that I want to put across is we established that we can write this in a shorthand form using the sigma notation that we learned in Appendix E. So that's the conclusion, that the true area is equal to what the limit as n approaches infinity. The n is the number of rectangles you're using, right? As we increase the number of rectangles, the area under the curve becomes accounted for, well accounted for. So as the n approaches infinity, we expect to get a true area, right? So it's just going to be a limit of sums, right? Using right endpoints or left endpoints. And then we could also use any sample point in between the subintervals. So we established all of this, right? I did a recap because the next problem is going to be based off on what we saw under the area problem. So this one is the distance problem. Now, to look at the distance problem, you first have to know the distance formula, right? So remember that distance is equal to velocity times time, right? Velocity times time. Okay. Now, the thing is, suppose you are driving, right? You are driving your vehicle and it says, let's say 40 miles per hour, 40 miles per hour. Well, what that implies is if you drive at the same 40 miles per hour, right, over an hour, if you drive at the same 40 miles per hour over an hour, you expect to cover out 40 miles. So for that one, if you're computing the distance, it's direct. You can just get it, right? It's just the velocity. Because the velocity is constant, right? You just multiply that by the time and you get the distance that you covered. But as you well know, when you're driving, usually your velocity will vary, right? The velocity will vary depending on the time. It will vary, right? It will vary within time. It's usually not, maybe unless you have a computer you program, but if you're human and you're driving, maybe there will be some parts where you speed a little, there's some parts you decrease your speed a little and so on. So it will vary within some time interval. Then the thing is, if the velocity is not constant, how do you calculate the distance that you covered at any point in time? Right, so that's the problem here. That's the distance problem, right? So for the distance problem, what you're going to do is something similar to what we did for the area problem, right? So what you're going to do is, so suppose the distance is, say we have a time interval, say 0 to 10, right? Say 10 minutes. Within 10 minutes, what is the distance you've covered, right? So the thing is, within 10 minutes, we know our velocity will vary. So we say, okay, the velocity is less likely to be varying within a shorter time. So it's more likely that you'll be traveling at the same velocity between 5 seconds than it is likely to be traveling the same velocity within the interval 0 to say 20 seconds. Please, I hope you get that argument. If you're moving, right, within a distance, if I give you like a second, it's likely that your velocity will be constant than if I give you traveling in 5 seconds. You see, so the thing is, what you're going to do here is we are going to, for say 10 minutes, let's say it's 10 minutes. What you're going to do is the velocity within the 10 minutes will vary. So to estimate the distance, what you're going to do is you are going to shrink the time interval. You're going to account for the time intervals in pieces. So for the 10 minutes, we can say, okay, why don't we take the velocity within, like, say, each let's say 1 minute, right? So we assume that, okay, within each 1 minute, the velocity is constant, so that we calculate the distances for each 1 minute and then sum everything up. And that'll give us the total distance. So that's the idea, right? So let's illustrate this with this example 4. That will show us exactly what's happening here. So this one says, suppose the odometer on our car is broken and we want to estimate the distance driven over a 30 second time interval, right? We take speedometer readings every 5 seconds. So the actual distance that is expected to be computed is within 30 seconds. But because the odometer is broken, right, we are measuring the speedometer and using the speedometer readings at every 5 seconds, so that we can compute the distance for every 5 seconds and then sum them all up and you get a total, an estimate of the total distance. Okay, so here are the readings, right? So the time is in seconds. So for the seconds, we have 0 to 5. So it's 5 seconds, right? 5 second interval. So 0 to 5, and 5 to 10, 10 to 15, 15 to 20, 20 to 25, and then 25 to 30, right? Now, these are the readings. Now, in this case, the readings are measured in miles per hour, right? They are measured in miles per hour. So that's 70 miles per hour, 21 miles per hour, 24, and so on and so on to 28. Now, these readings, so this just means that at time 0, oh, and one more thing, if you are not using your name to join, please do, because I'll take attendance, right? If you're using or if you use a name that I can't recognize, do let me know, send me a chat so that I'll see your name and mark you as present. Okay, now the first thing that we have to acknowledge is the units are not consistent. The velocity is in miles per hour and the time is in seconds. So the first thing is, let's try and make it like, let's calculate this velocity in seconds, right? So the velocity in some units per second. So the unit per second that we can do is, you can do it feet per second, right? So this table is just transformed into that, right? So that the units are consistent using this. So 1 mile per hour is 5,280 over 3,600 feet per second. So we computed this. So this is the table we are going to use. Okay. So let me create a little table here. So 0 to 5. So this time, this is the velocity. Right, 0, 5, and next is 10, 15, and then 20, 25, 30, right? And then within this time is 0, 25, so this 25, and then this 31, 35, 43, 47, 45, and then the last one is 41, 47, 45, right? Yeah. Okay, now the thing is, we have been able to break down the time intervals into much smaller intervals, right? So it's 5 seconds. Now, what we are just going to do is to estimate the distance covered. We need to try and get the, let me use a different color. No. We need to try and get, so we have the time. So within each time is 5 seconds, right? So within this time is 5 seconds. Within this time is 5 seconds. We have the time for each of the intervals. It's the same 5 seconds. But the question is, how do we pick the velocity, right? Now, to pick the velocity is going to be likened to picking using sample points in the area problem. So what we're going to do is we need to assume a velocity within this interval. Now we know that from 0 to 5, we traveled from 25 to 31. We started with 25, we left with 31. So one way we can do this is we can assume and say, okay, let us assume that the velocity that you traveled over that entire 5 seconds is the velocity you started with, right? Is the velocity you started the interval with. So for this first interval, 0 to 5, you say, okay, let's pick this velocity to be the velocity we are using for for this entire 5 second interval, so that we can compute the distance. So if you assume 25 to be the velocity within the first time interval, then the distance is going to be what? The distance covered in the first time interval is going to be 25 times 5, which is what you see here, right? And that'll give us 125 feet. For the second interval, we can also pick the velocity we started the interval with. So this is like using left end points, right? Left end points for your velocity, right? So for this second interval, you can assume and say, okay, let's assume that the 31 is what the entire velocity you use for the 5 second interval. So if there's a constant velocity within that 5 second interval, then the next distance, right, for the second interval is just going to be 31 times 5, which is 155 feet, right? For the third interval, right, we are using the left end point for the velocity. So you can pick 35 to be your constant velocity within that 5 second interval. And then you can compute the distance for that interval too. And then the fourth one too, you do the same. The fifth one, you do the same. And then the last one, wait, 1, 2, 3, 4, 5. Yeah. And then this one, the last interval, you pick 45. And for each of these, you calculate the distance covered. Another one will say, okay, why don't I use the velocity that I left the interval with to be my constant velocity within the interval, right? So for that one, you can use, let me use a different color, purple. Okay, so if I'm using the velocity I left the interval with, I'll assume that, okay, within that first time interval, the velocity I left with is 31. So I'm assuming that the constant velocity within the first time interval was 31. So I'll use this. So in that case, my distance covered will be what? 31 times 5. Right, so using it from the right, my distance covered will be 31 times 5. Plus, for the second interval, I'm assuming that the velocity I left with is what? Is the constant velocity that was traveling in that 5 second interval. So that my distance will be what? 35 times 5. I'll keep going, right? On and on and on. The next one will be what? 43. 43 times 5. The next one will be 47 times 5. And then plus the next one will be 45 times 5. And then plus the final interval, I'll use the right endpoints to what? To calculate my velocity. So that'll be what? 41 times 5, right? So you can either assume that you're using the velocity you left, you started the interval with, or the velocity you left the interval with to be your constant velocity within that interval, and then you can calculate the distance. Now, when you get the distance for each of the interval, just add them together and you get an estimate of the total distance. So that's the idea, right? So for the first one, you see that they have this, right? So this using the estimate of the total distance using what? Since they picked 25, then they were using the initial velocity you entered the interval with, right? They need the velocity you enter the interval with to compute the distance. So that's 25 times 5 and so on and so forth. So that's the estimate, right? And then for the other one, our other estimate is what? We assume that the velocity that we left the interval with was the constant velocity we're traveling within the interval. So that's 31 times 5, 35 times 5, and so on. That's the one I wrote down here, right? And then that one is also giving us this 1,210 feet, right? So that's the estimate. Now we know that the true area will lie in between these two estimates, right? The true area will lie in between these two. Now, the thing is, this is an estimate and we use only 5-second interval. Now, it's safe to assume that just like we had for the area problem, if you shrink the time interval, the more accurate this becomes. Because as I argued, if you're traveling within 1 second, like a distance with time 1 second, it's likely your velocity will remain the same than a distance of, say, 5 seconds, right? So that means that if I should shrink the time to be very, very small, then that means my estimate of my velocity will be very accurate. That is, the fact that it's constant will be very accurate. So the true distance formula will be obtained, the true total distance will be obtained if the time is approaching what? Infinity, right? If the time divisions is approaching infinity. So for the first case, for the example that we had, we partitioned the 30 seconds into what? Into 6, right? So 0 to 5, 5 to 10. So 1, 2, 3, 4, 5, 6. Yeah. 1, 2, 3, 4, 5, 6. Yeah. Into 6 intervals, right? So that means if I partition this time interval as that time interval approaches infinity, as the partition approaches infinity for the time interval, then I'm going to get my true total distance, because my assumption of the constant velocity within the interval will then be more accurate. Do you see? Yeah, so that's the idea. So is this the same as the area problem? Just as the instantaneous velocity was the same as the tangent problem. It's the same thing, right? So this one saying in general, suppose an object moves with velocity v, which is f of t, right? Where we have the interval a to b, right? T is in between a and b. And then the f of t is a non-negative function, right? And then we have velocity readings at time 0, t0, and then at time n, tn equal to b, right? And then we are calculating them at these time points, right? T1, T2 up to Tn, T0, T1, T2 up to Tn, right? And then we are saying that the velocity is approximately constant on each subinterval. So if we can divide it so that it's so small that the velocity is approximately constant, right? Now, how do you calculate this delta T? Well, it's similar to what we had for the delta X under the area problem, right? Delta T is just equal to what? The end time, which is the B, minus the initial time, which is A, all over the number of subintervals you want to divide this into, right? So that's N, right? So this tells us that this delta T, which is is going to be the width of that time interval, times the f of T0, that's going to be the estimate of the velocity at time T0, right? It's going to give us the distance traveled within the first interval, right? So if you have this f of T0, delta T plus f of T1 delta T, and so on and so forth up to this, then that's the sum. And don't forget that this is, you are using the left end points, right? You're using the left end points. So because the T0 is here, T1 is here, and so on and so forth up to T sub n, and then T sub n minus 1, right? So if you're using the left end points, then for the first interval, you are picking T0 to give you your velocity. So that's why we have f of T0. Don't forget f of t is a velocity function, from here. So if you use T naught, then f of T naught is your assumed constant velocity within that interval. And then times what? This delta T, which is the width of the time interval, right? And then plus for the next interval, which is the second one, you use the left endpoint, so that'll be T1. Then times what? Delta T, and so on and so forth. For the last interval, since you're using the left endpoints, you'll be T sub n minus 1. And that is what you see here. That's giving us the velocity, the constant velocity within that interval, and then times the width of that time, which is the same. Delta T is always the same, right? So in sigma notation, from what we learned, we can write this in a shorthand way, right? Just simplify this as this. So you have the sigma I from 1 to n of f of t sub I minus 1 delta t, right? In the same case, we can use the right endpoints for the velocities. So for that one, if you're using the right endpoints, you have t sub 0, t sub 1, t sub 2, and so on and so forth, up to t sub n minus 1. And then the last one is t sub n. If you are picking the right endpoints to give you your velocity within that time interval, then for this first interval, you're going to pick what? T1 to give your velocity times what? The time interval. The weight of the time interval is delta t. It's always delta t, right? So delta t. For the next one, you use t sub 2 to give to calculate the velocity for the second interval, and delta t, and so on and so forth. This simplifies to what? That sigma notation. So as I said, it's the same as the area problem, just that this one you're dealing with time, right? And then the function could be a velocity function. Yeah. Please, any questions so far? Anybody needs time here? Okay. Now, the true total distance, right? The exact total distance will occur when we have the n approaching infinity. So we divide the weight of the time interval such that is approaching infinity. Because the smaller the time intervals, the smaller the weight of the time intervals, the more accurate our assumption of a constant velocity is, right? As I said, velocity is less likely to change within a shorter interval than it is within a longer interval. So if we want the velocity to be constant, then we need the time interval to be as small as possible. And that will occur if we divide the time interval into as small subintervals as possible, which implies that n is approaching infinity. The subinterval division is approaching infinity. So that's the best case scenario, right, to get the total distance. All the other ones are just estimates, right? So that's limit as n approaches infinity of this, either the left endpoints or the right endpoint. They'll give you the same results, right? So that's how we compute the total distance, the true total distance, right? So the exact distance, right? True total distance. So they will all reduce to appendix E, the last problem that we solved, the limit of sums. Do you remember that? I told you to pop up in chapter 5, the limit of sums. They all reduce to the limit of sums for the true either area or true distance, total distance covered. They are all limits of sums. Now, please, that's the end to this 5.1. Do you have any questions here? Okay. Then let me save and let's move on to 5.2. Now for 5.2, let me tell you right ahead, is the longest slide list in the whole of calculus, at least for this one, the one that I have. I'm sharing the 5.2 slide. It's about 50 or so. Yeah, 50, exactly 50. But a lot of it is like notation and stuff, right? You're going to define stuff. You're going to see some notations. You're going to calculate some area stuff, yeah, that you see. So this is just for you to be aware of what you're going to face. So this one, 5.2, is a lot of definitions. I'll just be defining stuff, yeah, and then I'll be calculating at the long part. So you're looking at the definite integral, right? Now, 5.2 is based off on a lot of stuff that we've learned in 5.1. Now we're going to have a definition for some of the stuff we've seen in 5.1. For 5.1, we said that this limit, the limit of sums, is the same as the exact area or the total distance, the exact total distance, right? So it pops up in those two cases, in those two problems, right? So we said the limit as n approaches infinity of this sum, I from 1 to n of s, f of x sub I star. So that means that's a sample point, right? Delta x, that's equal to this. So you write this in a series form, right? This gives us what? The area or the total distance when you're talking about the distance problem, right? Now, this one says, it turns out that this same type of limit occurs in a wide variety of situations, even when f is not necessarily a positive function. So it's similar to what we did for derivatives. You see, when we said, oh, the slope of the tangent is the limit of what? Secant slopes. And then the instantaneous velocity is a limit of average velocities. Do you remember? And we said that that same limit occurs in several fields. It's an instantaneous rate of change. So it can be likened to this part in the sense that this limit of sums doesn't just occur under the area problem or distance problem. It reoccurs in several places. So that is why there is a need to get a definition. So that's why under the derivative, we said, oh, the derivative is that limit. So for here, we are going to talk about this limit of sums, and we are going to define it as something because it reoccurs in several fields, so that we don't have to be talking about the total distance, when is distance. We don't have to talk about the area under a curve when we are looking at that, right? We can just refer to it in general terms, and then wherever whatever function we are dealing with, we know what we are talking about, right? So it turns out that this limit of sums is called a definite integral. It's called a definite integral. So let's look at the definition. And perhaps let me make this bigger so that you see it well. Okay, so this one says if f is a function defined on a closed interval, so we have it from a to b, right? And then we divide this a to b into n sub-intervals of equal width, right? So that's delta x equal to b minus a all over n of equal width, right? Our x sub 0 equal to the a, which is the initial, the first point, right? The lower bound. And then our s sub n is the upper bound. So they are the endpoints. And then let s sub I be the sample points. Then we define this limit of sums to be called a definite integral, right? So instead of writing this tedious limit of sums thing, we can write it as an elongated s, and then bring down the lower bound, right? That's the a. And then write the upper bound here. And then you know the function form is what? Is f of s sub I. That's what we used to compute the height of the rectangle under the area problem, or the velocity under the distance problem. So that's just going to be the function. This time around, you don't do sample point symbol. You just do x. And then you write this kind of like this dx has no direct meaning, but you can think of it that it replaces the what? Delta s. Remember we said it's the same as the delta x under the what do you call it? Differentials. We talked about it in differentials. I think that was 2.8 or so. Yeah. So that's it, right? So this is how you write it. Now, when this dx is there, the x part tells you that, oh, the variable that we are looking at in this function is what? Is x. It shows you the independent variable here, right? So if this is saying t, then that means the f of x will be like a constant. The f of x has to be f of t, so that we know the thing depends on this integral. So instead of this limit of sums, you can just write it as this, and that's the notation we'll be using. And that's what we call a definite integral, right? Now, this integral is a definite integral, right? And sometimes the limit may not exist, right? But provided the limit exists, right, then it gives the same value for all possible choices of the sample points, right? If the function exists, then we say that f is integrable on the closed interval a to b, right? So these are terms. As I said, for 5.2, it's a lot of terms and stuff, but they are going to be very important moving forward. Please, any questions on this definition? Okay. Now, the symbol elongated s here you see is called the integral sign, right? It's the integral sign. It was introduced by, you all remember Leibniz, right? One of the proponents of calculus, one of the fathers of calculus, right? So Isaac Newton was the other one who was credited, but he is the one who brought this symbol, right? So it's more like an elongated s, which is sum, right? It's a limit of sums. So it's kind of like, I don't know why they stretch it by limit of sums, right? So s elongated, right? Yeah, limit of sums. So that's the definite integral. Okay. Now, the thing is, for this notation, this f of s is called an integrand, right? An integrand. And then a and b, which are here, are called the limits of integration, right? A is the lower limit, and then b is the upper limit, right? So just note these. From now, I'll be using these terms, and then you should know what I'm referring to. Okay. Now, this ds has no meaning in itself, but it tells you which independent variable we are dealing with, as I told you earlier on, right? Now, the procedure of calculating this symbol, this integral, is called integration, right? This is called an integration. Anybody needs time here? Any questions? Okay. Now, one thing that you have to know is, if we have a definite integral, say we have you have the integral sign, right? A, and then the limits of integration a to b f of x dx. Then you can just change this, the x here, the independent variable, and it doesn't change the integral, right? So if you have this, and then I change it to f of t and then dt, as long as I change these two, the variable at the end of the differential, right? And then the variable in the function here, it doesn't change the definite integral, right? So I can change it to r dr, f of r dr, as long as you have a to b. If it's f of m dm, it's the same thing, right? It's going to be the same, it remains unchanged. Okay, now we saw this sum in 5.1, right? This was the one that we were using for calculating an approximation to the area, or the approximation to the distance, the total distance. It turns out that this one has a name, right? This is called a Riemann sum. It's named after a German mathematician, Bernhard Riemann, right? This is called a Riemann sum. Okay, so these are things you have to know, so that when I say, oh, Riemann sum, blah, 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 you know what I'm talking about. You see, Riemann sum of something, you know what I'm talking about. Yeah, so this is a Riemann sum. So the definite integral is just a limit of what? Riemann sum, kind of. You see, yeah, it's just a limit of Riemann sum. Please, anybody needs time here? Any questions? Okay. Now, you know that for Riemann sum, it's just used to approximate, right? So for a Riemann sum, you need to determine your sample points, right? So your sample point could be a midpoint, it could be a left endpoint, it could be your right endpoint, or so on. We saw a lot of this in 5.1, right? So this is what this graph is showing. Okay, so let's see. So we can see that this is, okay. So now, if the function is positive, or let's say non-negative in general, if the function is non-negative, like you see here, then this one can be interpreted as what? The definite integral can be interpreted as an area under a curve, right? It can be interpreted as an area under a curve. However, if the function is not entirely positive, or in other words, the function is also, it includes a positive part and then a negative part, then as you can see, when you're calculating the approximation using the rectangles, these rectangles, which are underneath the x-axis, right? These ones, they'll give you a negative area of a rectangle because their height will be negative, right? So when you check the height from here to here, right? When you read the height, it's going to give you a corresponding negative value. So the area here will be a positive value, which is the width times the height, which is negative. So that will give you a negative value. And then this will also give you a negative value. That will also give you a negative value, and so on. All the ones underneath the x-axis will give you a negative value. On the other hand, those above the x-axis will have a positive height. Hence, they will give you a positive area. So in the end, you see that you'll be adding these two since they are positive. But then, since these are negative, when you add a negative, you end up subtracting. So we say that if the function is not strictly positive, or the function is some part negative, some part positive, then we can interpret the definite integral as what? As area under a curve. We will end up doing a subtraction of the areas. So in that case, we refer to the definite integral as a net area. It's going to be a net area because it's going to be a difference in areas, right? So it's going to be the positive part of minus the what? The negative part. Please, are you okay with this? Okay, so just definitions and stuff. Any questions so far? Okay. Now, another thing, some functions, not all functions are integrable. Not all functions are integrable, right? But then this is a theorem which illustrates when a function is integrable, or defines when a function is integrable. So the theorem says if f is continuous, if the function is continuous, or if f has only a finite number of jump discontinuities, right? Then f is going to be differential. Why do I keep saying? F is going to be integrable on that closed interval, right? So as long as if the function is continuous, or the function has only a finite number of jump discontinuities. I hope you remember jump discontinuities. Let me show you briefly what they are. All right. In jump discontinuity. Right. I hope this rings a bell. Discontinuity. Yeah. So when we had this kind of limit where the function is defined at a point, but the limit does not exist because the left endpoint and the right endpoints are not equal, then we have a jump discontinuity, right? So if there are only a finite number or the function is really continuous, then the definite integral will surely be defined. In other words, the function will be integrable. So the limit will exist. The limit of something will exist for sure. Okay. Now, it doesn't matter the sample point that you choose, right? No matter the sample points, as long as the limit exists, right, you get the same value for the definite integral. So you can use right endpoints, left endpoints, midpoints, or any other sample point, right? As long as the limit exists, then you get the same thing, right? Okay, please, any questions on this? Now, this is going to be very important when you're evaluating integrals here. When you get to 182, for that one, they will show you cases where the function is not continuous and how you're going to solve it. But whenever you're doing a definite integral, you first have to make sure that the function is continuous. We'll talk more about it in 5.3, 5.4. Okay, so now this is the theorem, right? So we've established this. How do we calculate this? That's the question. How do you calculate a definite integral? We just define it. So from first principles, do you remember how we did the f prime of x? What is f prime of x? The f prime of x go to the limit as h approaches 0 of f of s plus h minus f of s all over h. Do you remember that? From first principles. That's the same with what? A definite integral. So the limit of sums is the first principles idea of how to solve a definite integral. So if you are given a definite integral, you'll be doing limit as n approaches infinity of what? Of the sum. Okay. So because we know that this, as n approaches infinity, our sample points could be right endpoints, left endpoints, or any other point. We can say, okay, in order to compute this, let's use right endpoints to calculate this limit of sums for the definite integral. So the delta x is still the same. It's just b minus a all over n. And then we established in 5.1 that the x sub I will be what? A plus what? I delta x. Now let me just talk briefly about this so that you see what I'm talking about. We said that s naught is the a, right? And then Sn is equal to the B. And in between these two, we have so S1, X2, X3, going on and on. You have Sn minus 1. And then I told you that from the last time that if you have, how do you get the next point, right? If you have the first point, say A, how do you get to X1? After computing the width, you just add this delta x to the A, right? So X1 is just A plus delta x. Right? So that you get the next point, right? Whenever you compute the width and you're partitioning the time in like the interval into sub-intervals, you calculate the width and you keep adding the width to get the next point, right? So for x sub 2, how do you get x sub 2? X sub 2 is just going to be x sub 1 plus the width so that you get the next point. But then x sub 1 is a plus what? A plus delta s in itself. And then we have another plus delta x here. So that's what is giving us a plus what? 2 delta x, right? So in the long run, in general, right, whenever you want to calculate s sub I, then it's just going to be a plus what? This 2 is when the the sub number is 2, right? This one is s sub 1, that is like 1 delta x. So if you want s sub I, it's just a plus what? I delta x, right? So you can calculate this s sub I and plug it in the function, and then you'll be able to take the limit of the sums. All right, so that's how you compute it from first principles. We won't be doing a lot of this, right? At least I'll show you one example of how we do it. But then that will help you appreciate the shortcuts more when we get on 5.3 and 5.4. Yeah, but please, any questions on this structure? Anybody needs time here? Okay. So this one says, express this as an integral on the interval 0 to pi. So for this one, please help me out. I want to get the definite integral representation of this limit of sums. How am I going to write it? We are not solving the problem. We are just looking at the symbol here. So how do I write this? Remember that a to b of f of x dx is equal to what? The limit as n approaches infinity of delta x I from 1 to n of f of s sub I star and then delta x. So if we have this, then how am I going to write this as an integral? Okay, let me start. So my question is, what's going to be the upper limit of integration? Anybody? Battery is almost down. Let me put this in. Okay, I have some charts. Let me see. Pi, perfect. Thank you. Thank you, Megan. Yeah, so remember that the interval is from what? 0 to pi. 0 to pi. So this is the A, this is the B. Right? And then the B always goes here, is the upper limit. So that's pi. And what about the lower limit? Zero. Thank you, Sage. Thank you. Yeah, so 0. And then how will I write this thing? Remember that the s sub I star is no longer there. It's just f of x. So what will I write down here? Anybody? What will I write here? It's just the notation, yeah. So please give it a shot. What do you think? Anybody? Perfect. Thank you, Jessica. That's perfect. So that's x. It's just that you change the s sub I to x. That's all, right? Or the function in front. So that's just x cubed plus x sine x. And then finally what? Dx. Please don't forget that. Very important. You have to bring it. And that's it. You are done. Right? So that's how you change it from whenever it's limit of sums to a definite integral. Right? So this just explains. There's a typo here. It's 1, but it's supposed to be plus. Okay. Please, any questions so far? Okay. So this is just talking about how you change it, right? So if you have the limit of the sums, just elongate the s, look at the interval that you are taking the limit from, right? So A to B, those will be your limits of integration. Change the s sub I star to just x, and then write it down, and then you just add the dx. That's all. Okay, now let's look at evaluating integrals. So this is where you're going to use the limit of sums thing. Hopefully I have some time to solve this. This is going to be a long one. Okay, now remember I told you in Appendix E that this will come up. Remember this one by that 10-year-old guy, the sum of the first and positive integers. So this is you have the sum of the square of the first and positive integers. You have the sum of the cube of the first and positive integer. So these will come up because you'll be doing limit of sums, right? We also remember these ones, right? They will come up for sigma notation. Now let's look at example 2. I'm not sure if I'll have time to do the 2, especially the B. The B is going to be a long one, but let's start and see where we'll get to. So this, you're on 5.2. This is example 2. Okay, I have this down. Okay, so A, we have the function f of x given by what? S cubed minus 6x. And then the A is equal to 0, B equal to 3. And we are using 6 subintervals. So it says, evaluate the Riemann sum for this, taking sample points to be right endpoints. So sample points are right endpoints. Okay, so let's do this. So let's start. We are looking at the interval from where? 0 to 3. So I just write it down. Now, to get the subintervals, I just need to find a width. So I need delta x. So delta x is b minus a all over n. So what's your b? B is 3. And what's your a? A is 0. What's your n? N is 6. So that means you have 1 over 2. So you keep adding 1 over 2 to the subsequent points, and then you get an s point. So 0 plus 1 over 2 give us half. Half plus 1 over 2 give us 1. 1 plus 1 over 2 give us 3 over 2. 3 over 2 plus 1 over 2 give us 2. 2 plus 1 over 2 give us 5 over 2. And then 5 over 2 plus 1 over 2 give us 3. So how many intervals? Let's see if we have the same subintervals. 1, 2, 3, 4, 5, 6. Nice. You've done it. Okay. Now with these intervals, what it's saying is use the right endpoints. Use the right endpoints. So that means for the first interval, I'll use this sample point to get my height. For the second interval, I'll use this sample point. For the third interval, I'll use this sample point. For the next one, I'll use this. For the next one, and the last one, I'll use this. right? So the width is 1/2, and then the height is what? Is determined by the right endpoints. So now let's calculate this. So the estimate, the Riemann sum, don't forget the Riemann sum is just what we were doing in 5.1. It just has a name now. It's called Riemann sum, but the idea is the same. So the Riemann sum, in this case, since we're using right endpoints, we call it R. And then the subscript is the number of subintervals, which is 6. So R sub 6, right? R sub 6, this is too big. R's, I'll need more space. R sub 6, yeah, somewhere here, yeah. R sub 6. So R sub 6 is going to be, for the first subinterval, the width is always half. So I can even factor that out and then calculate the height for each of the intervals. So for the first one is f of half, right? It's f of half. That'll give us the height. And then for the next one, it's f of 1. So let me just keep going until I get to f of 3. So the next one is f of 1. The next one is f of 3 over 2. The next one is what? F of 2. The next one is what? F of 5 over 2. And then the last one is what? F of 3. Please, I hope you follow. Any questions so far? I hope it makes sense. If you don't understand, feel free to to let me know. I'll try and explain it again. Right, so we have this. Okay, so now when you get this, you just have to solve for these values from the function. Right, so f of half, let me do an example here so that you see what I mean. F of half, we know f of x is s cubed minus 6x. So f of half is just going to be half cubed minus 6 times half. And then you get a value for this, right? If you want f of 1, I think that one would be easy to evaluate. So that would be 6 times what? 1. So that, oh no, minus. And that's equal to, that's -5, right? So you do it for all of them, right? So if we do it for this, do it for this, do it for that, right? So you get R6 to be equal to, since this one demands a lot of calculator work, I won't ask you to do this directly on a test or anything. But I won't ask you to do this. It's a lot of calculator work. On your homework, you are free to use your calculators, right? So in the long run, you're getting half. Then the solution is already on the whiteboard. Sorry, on the PowerPoint. So let me write the answer. Yeah. So we get -3.93. So half. The first one is -2.875. And then -5, which is what you computed for f of 1. Then -5.625. And then -4. And then plus 0.625. And then plus 9, final one. Right, so in the long run, when you calculate everything, oh wait, is someone asking a question? Why do we take out the half? Oh yeah, that's a good one, Nicholas. So the reason why I took out the half is, let me write the answer, right, to this one. So -3.9375. So that's the final answer for the estimate. Now the reason why I took out the half is, for this first interval, how do you calculate the area? The area is going to be, the area of the rectangle is what? Is the width, which is half, times the height, which will be obtained by using this half sample point. So that'll be f of what? Half. For the next interval, the width is still the same. It's half times what? The height, which is obtained by doing f of 1. For the third one, is half times what? F of 3 over 2. For the fourth one, is half times what? F of 2. For the next one, is half times what? F of what? 5 over 2. And then for the last one, is half times what? F of 3. So this half is always there for each of the terms. So I'm just factoring it out so that I don't have to write half f of 2, half f of half, half f of 1, half f of 3, half of f of 3, and so on. Because the width is always the same. So just bring it out and do the height computations for each of them. So that's why I did that. Does it make sense now? Nice. Okay. Let me see if there's still some time. Okay, 2 minutes. But please, you understand this. Do you have any questions here? Okay. I don't think we'll end the B part, but let's start. It's going to be fun. At least we'll set it up, and when we meet the next time, we solve it. Okay, so let me go. Yeah. So the function is, let me erase. Let me go back to the question. Oh, yeah. So the question says, find this, evaluate this. right? So I'm going to set it up, and then next time we meet, I'll solve it because it's too long to finish solving everything. So you have 0 to 3, 0 to 3, and then x to the cube minus 6x dx. So for this one, we need to evaluate this from first principles. It's kind of like doing the differentiation using the derivative, the definition of a derivative. So how do we get this? Well, we have to first change it to a limit of sums, right? So this has to be a limit as n approaches infinity of delta I from 1 to n, and then f of what? S sub I. You can use the right endpoint. So f S sub I and then delta x. But the thing is, what is S sub I? S sub I is a plus what? I delta x. Okay, so now let's do this. For the interval 0 to 3, what is delta x? It's 3 minus 0 over n. So that means you get 3 over n. What is a? A is 0, and then b is 3. So that means that our S sub I will be equal to what? 0 plus what? I times what? Delta x, which is 3 over n. So that means S sub I is 3i over n. A lot of professors like to give a lot of these questions, like doing this from first principles, but we just look at it once and then that's it. Okay, so we have this. Okay, so what do we do? Now, the limit of sums will then become limit as n approaches infinity of sum I from 1 to n. What is f of S sub I? Now, if S sub I is if S sub I is 3i over n, then f of S sub I is just f of 3i over n, which is equal to what? That's going to be 3i over n cubed minus 6 3i over n, because we know that f of x is what? S cubed minus 6x, right? So just plug the 3i over n in there in place of x and you get this. So that means we finally have 3i. Please give me a sec. I'm done. I'll write this down. And then next time we meet, I'll solve this. So 6 times 3i over n, right? And then what's the last piece? So we have this piece, right? That's this. So what's the last one? Delta x. And delta x is 3 over n. So we have to solve this limit of sums, which we will continue the next time we meet. So next time we meet, I'll just write this down and then we solve this. So that's the end of today's lesson. Thank you very much for your time and for giving me some minutes to wrap this up. Next time we meet, we do this, which is on Monday. Have a nice weekend. All the best. You're welcome. But if you have a question too, you can stay and I'll be around. You can ask me, I'll explain further, especially how I wrote this down. You're welcome.